You know the incredible rise of AI that we're all watching? Well, it's on a collision course with the hard physical limits of silicon. The very foundation of computing is, frankly, groaning under the weight of these new trillion parameter models. And that's exactly what we're going to dive into today, the revolutionary tech that's about to completely shatter that physical wall. To really get the problem, you just have to look at this. I mean, it says it all. Over the last couple of decades, our processors, our ability to compute, shot up by a staggering 60,000 times. But our ability to actually feed those processors data from memory, that's only gotten about 100 times better. This right here, this is the great mismatch, and it's creating a massive traffic jam right at the heart of every single AI system. And this traffic jam, it has a name, the memory wall. It is absolutely the villain of our story today. Just imagine you've got the world's fastest race car, but you can only refuel it with, like, an eyedropper. That's exactly what's happening to our most powerful GPUs. They're literally just sitting there, idling, starved for data, while they're trying to process the petabytes of information that modern AI demands. Now, what's so wild about this is that it reveals our second villain, energy. Moving all that data around with good old electricity is just incredibly inefficient. In fact, if you look at the chart, the energy we spend just shipping bits of data from memory to the processor, well, it often costs more than the energy we spend on the actual computation itself. We're spending more power on logistics than on thinking. That, my friends, is just not sustainable. So this leads us to a really critical question, right? We're scaling AI at this exponential rate, but the physical infrastructure, it's hitting these fundamental limits of physics and energy. So what happens when AI's progress just runs out of road? Do we just stop? Well, no, of course not. We change the road itself. The solution is to move from electrons to photons. We are talking about computing with light. And look, this isn't science fiction. It's what the industry is calling a photon-electron convergence. And it is absolutely the hero of our story. Okay, but let's be super clear about something. This is not about throwing out all our silicon chips. It's about creating a hybrid system. Think of it like a smart division of labor. We let photons, particles of light, do what they do best, which is communicate data over distance almost instantly and with very, very little energy. And we let electrons keep doing what they do best, performing all the complex logic inside the processor cores. So how does this whole revolution actually happen? Well, it's not one single invention. It's happening across three main vectors. First, and this is the most immediate one, we have optical interconnects, basically just using light to move data around. Second is optical switching, using light to actually rewire the network itself on the fly. And third, the most futuristic one, is optical computing, using light to actually process information. All right, so let's start with the one that's happening right now, the most mature and impactful one, the interconnect revolution. This is all about completely rewiring the brain of our AI data centers. For years, we've used these things called pluggable optics. You know, little modules you just stick into the front of a server. But just look at this table. The whole industry is moving to something called co-packaged optics, or CPO. By putting the optical engine right next to the processor on the very same package, we just slash the distance data has to travel. And the results, as you can see, are totally transformative. Power efficiency gets way better, latency, or delay, plummets, and you can pack way more data pathways into the same space, sending bandwidth density through the roof. And this shift has kicked off a whole new generation of really cool startups. So first up is Lightmatter. Instead of connecting chips with a bunch of messy cables, they're building something called Passage, which is this massive programmable optical circuit on a single silicon wafer. You literally attach thousands of GPUs right onto this wafer, and it connects them all with light, basically creating one giant unified computer with zero internal cables. And building on that idea is our next player, Celestial AI. They're tackling that memory wall head-on with their Photonic fabric. Their tech lets thousands of GPUs access a giant remote pool of memory as if it were sitting right next to them. This is something called memory disaggregation, and let me tell you, it's a huge deal for training models that need way more memory than you could ever fit on a single GPU. Then you've got IR Labs, and their approach is really smart. They take a modular approach with these little terafissy optical chiplets that you can package with any processor. But here's their brilliant trick. Putting a laser right next to a 1,000-watt GPU is a recipe for disaster. Lasers absolutely hate heat. So IR Labs moved the laser off chip to this external source they call supernova, which then pipes in cool, clean light through fiber optics. It just neatly solves a massive thermal headache. So beyond just connecting chips, light can also reconfigure the entire network itself. Companies like Google are already using optical circuit switches in their TPU supercomputers. These devices use an array of microscopic mirrors, like literally tiny mirrors, to physically redirect beams of light, changing the whole data center's network layout in milliseconds. This lets them perfectly tailor the network structure for whatever AI model they're running, which boosts efficiency like crazy and can even route around failed hardware in an instant. Okay, so we've moved data with light, and we've rewired the network with light. But what about that final frontier? What about actually thinking with light? This is the quest for optical compute. And this is where things get, well, a little tricky. See, using light for computation is incredibly energy efficient. I mean, the core math operation can be literally zero energy. But there's a catch. This is analog computing, and it's noisy. It really struggles to get the high precision that our digital electronic chips just take for granted. We're talking like 4 to 8 bits of precision compared to the 16 or 32 bits that AI models are used to. For years, that precision problem was a complete showstopper. But now we've had a breakthrough. Researchers from IBM and ETH Zurich pioneered this concept called hardware-aware training. So instead of trying to build perfect, noiseless analog hardware, which is maybe impossible, they just teach the AI model itself to be resilient to the noise. They're adapting the software to the hardware's flaws, which is making analog optical computing commercially viable for the very first time. And the payoff for solving this? It is absolutely staggering. Just look at this chart. A top-of-the-line NVIDIA H100 GPU gets you somewhere between, 3 and 10 trillion operations per second per watt? But some of these optical architectures, like diffractive deep neural networks, they can reach an incredible 160 TOPS per watt. That is an order of magnitude leap in energy efficiency. It's just a completely different league. So when you start putting all of these pieces together, the interconnects, the switching, and now the compute, you start to see the dawn of a new era. An era where the substrate of intelligence is being built not just from silicon, but from light. And look, this isn't some far-off pie-in-the-sky future. This roadmap shows just how fast this is all happening. The interconnect upgrade, it's happening right now, through 2026. These wafer-scale fabrics and memory disaggregation, they're set to hit volume production by 2027, and by 2028, we are going to see the first dedicated optical compute cores, taking over specific AI tasks. This whole revolution is unfolding over the next 3 to 4 years. The real takeaway, the thing that it all boils down to, is a massive, massive drop in the energy cost of intelligence. Today, moving a single bit of data can cost around 20 picojoules. With in-package optics, we are driving that number down below 2 picojoules per bit. That's a 10x reduction in the energy tax we have to pay just to move information around. So why does this all matter? I mean, what does this new photonic foundation actually unlock for AI and AGI? Well, for one, it completely shatters the limits on context windows. It makes training these massive, trillion-parameter mixture of experts models not just possible, but efficient. It makes the insane energy demands of AGI actually economically feasible, and it enables the ultra-low latency you need for true real-time agentic AI that can interact with the world at human speed. Let me put it another way. With today's technology, an AI's working memory is kind of like a single book on its desk. With a photonic fabric, that AI now has instant access to an entire library. The implications for reasoning, for creativity, for problem solving, they are absolutely profound. Which really brings us to this powerful final idea. For the entire history of computing, the speed of light has been the ultimate unbeatable physical limit. But with these new architectures, it's not just the limit anymore. The speed of light is becoming the system's bus speed. So, we'll leave you with this final thought to chew on. We are fundamentally rebuilding the physical hardware of intelligence from the ground up, swapping out electrons for photons. The question we should all be asking ourselves is this: what new kinds of thinking will become possible when the machine literally thinks at the speed of light?